Hi everyone, how you guys doing? First of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy where everything is being taught to you completely in English. So this is a series that we are hosting for a revision, which is meant for revision for JEE 2021. So everybody who's going to give their JEE in a few months, this is a series that will help you revise key concepts quickly and practice some problems. Okay, so today the topic that we are going to discuss is work, power, and energy. Okay, and this is part one of the review. So before we get started, let me introduce myself for those of you who don't know me yet. So my name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and for almost past 8 years, I've been teaching physics for the IIT JEE Mains and Advanced exam. So I myself was All India rank 447 and All India rank of 192 in the two stages of the IIT JEE that I took. I also qualified the NDSC Stage 2 examination, and I was in the top 1% in the NACP. And as I told you, all this teaching so far had been offline, and offline I've been associated with some of the topmost institutes where I coached many students, top ranks in the JEE exam successfully. So now I hope to continue doing that here online with you guys. So moving forward, how can you guys make sure that you are also getting those top ranks that you aim for or you dream for? So you can get yourselves the Unacademy subscription. This subscription will give you benefits like live classes where you get to interact with your educators on a regular basis. Then you also have live polls and leaderboards which keep these classrooms highly interactive. You are also part of a test series session where you will have analysis of where you're lagging so that you are on your toes. You know where to put in extra hard work. And of course, you have live doubt clearing sessions. So for all Unacademy courses, every fourth session is supposed to be compulsorily a live doubt clearing session after every three teaching sessions. Whatever doubts you have about theory, about practice, so all of those doubts will get resolved in these sessions. So hello guys, hi Rajesh, hi Mahiji, how are you people? Okay, so physics Kamboj. Oh, my views on. Okay, so I don't know, I don't know much about him. So to tell you my views. Okay. In any case, I'm not here to share my views on others. I am here to share my knowledge and expertise of physics for the JEE exam. So that is what I think you should also bother about. It doesn't really matter what I think about anybody, right? It's you students who should see wherever you are learning well. I think that's great for students. Okay. Anyhow, so as I said, yeah, yes. So I told you. So this is mainly an educational platform to help you get a better preparation for IIT. So let's avoid comparing people or commenting on others. Okay, so I don't want to involve in that. Anyhow, so as I was saying, with the Unacademy subscription, you are also getting the chance to study from the top educators all across India from the comfort and safety of your home. Okay, so that is a huge advantage. Next, uh, these are the online courses on Plus which are happening now, which are being hosted by the JEE English team, and you can be a part of them by getting the Plus subscription. So there are three courses which are going on for class 11 topics, and then you have Hi Sakshi, how are you? Then you have four more courses for class 12 topics, which will help you boost your JEE preparation. All right. So how do you enroll in these courses? How do you make sure that you are getting the best possible education? You can get yourself the Unacademy subscription, and this is how you do it. You install the Unacademy app. Once you've done that, you go to the plus section of the app, select your goal as IIT JEE, and then click on that Get Subscription button. Once you do that, you will be redirected to a payment page where you will realize that the pricing of this Unacademy subscription has been kept very moderate compared to any fees that you pay at any offline institute. So get yourself the subscription and get ahead of others in the race for IIT. All right, and this is. Let me also remind you that Unacademy is also bringing you the Unacademy Combat, which is the most competitive gamified version for IIT Battle. So take part in this live, and if you do well, you will win yourselves a lot of rewards and prizes. So you can the next J Combat Unacademy Combat is going to happen live on 22nd of November. You can enroll now or using the code RD Live. So best of luck from my side. Take part in this, do well, and get yourself some attractive prizes. Good evening, Amod. How are you? Those of you following us on the YouTube channel of JEE English, can connect with us on the Telegram app using this link so that you're not missing out on any of the lectures or sessions happening here. All right, so without any delay, let's get started with the review of work, power, and energy. So first, we will talk about work, how work is defined, and then we will go on to discuss the concept of energy, and then we will see how the concepts of work and energy help you towards problem solving and how we can use these approaches to easily solve some of the most complicated problems. Okay. So talking about work, you will realize that if you talk about a constantly accelerated motion, then constantly accelerated motion is governed by an equation which is v square minus u square equals to a dot s. Okay, now if you multiply both sides with m, then m times a becomes f according to Newton's law. So the equation that you have is 2 times f dot s equals m times v square minus u square. So what you realize is that fine, according to Newton's laws, any force can change velocity. Okay. But if you talk about the change in speed is being measured by the term v square minus u square. Okay, so that is measuring the change in relating the speed, previous speed and the final speed. So this change depends not only on the force but on the dot product of force and displacement. So this brings our attention to this new term, which is the dot product of a force and displacement, and that is why we talk about it separately and we define it and we call it work. Okay, I hope you realize this is where we get the idea of defining something which is work, which controls the change in speed of objects. Okay, so for a constant force, the work done is defined as F dot S. Okay, its SI unit is would have been Newton meter, but we give this a special name. We call it joules. Okay. Now, please note that there's a lot of confusion among students that what is this F dot S? So I wanted to clarify, and I will just after talking about some more things about work. So work, you will know, is a scalar quantity. Now work can be positive, negative, and a zero. Why? Because you will realize work was defined as F dot S. So F dot S, the way you define that is magnitude of force times magnitude of displacement times cos of theta, where theta is the angle between the displacement vector and the force vector. Now, this magnitude of force is always positive. This magnitude of displacement will also be always positive. Now, the cos of theta, that you know that the angles between two vectors range from 0 to 180. So, in this range, cos theta can vary from +1 to -1. So, depending on the sign of theta, or cos theta rather, the work that is done on any object can be positive, negative, or zero. What is the implication or what is the meaning of a positive work or a negative work or a zero work? Okay, so Lokesh says, hi sir, even now I'm unable to get the PDF notes. I'm telling truth or else right now. Go to our channel and show PDF notes. Okay, lecture, please, sir. Okay, so Lokesh, just to let you know, I just talked to the team in the afternoon. I know I have been tracking this as well. And I told you that for the past 1 week, the team was having an off. Okay, so yeah, everybody had an off due to the festivities. Okay, so I have spoken to the team today afternoon itself, and I've told them to upload, and I have reminded them that I have already uploaded the links. Okay, I shared the location of the links that I had uploaded. I have reshared it, and I've asked the team to upload those PDFs. So don't worry. I think by tomorrow or maximum day after tomorrow, those PDF files which you had requested would be available. Okay. So I don't know why this delay was there. This should have been uploaded, but don't worry. I am personally keeping a track of that, and those PDF files would get uploaded within 2 days. That is my guarantee. Okay, so don't worry about it, Lokesh. All right. As I said, so what is the meaning of positive work? What is the meaning of negative work? And what is the meaning of zero work? So if you want to see what is work, so as I said, this work is defining how much the speed can change. Okay, work done by a force is telling you that how much that force can change the speed of an object. Okay, so when you say a work done by a force is positive, that means that the force can increase the speed of the object. If you say work done by a force is negative, that means that force will decrease the speed of an object. And zero means that such a force can have no effect on the speed. Okay, no problem, Lokesh. Most welcome. Okay. So that is what the meaning of positive, negative, and zero works are. Okay, whether a force can speed a particle up, whether it can slow down a particle, or it will have no effect on its speed. Okay. Now, please note that this quantity, the new quantity that we're talking about, work, it depends on the reference frame. Now, your forces are independent of your reference frames. I hope you know that. Okay, so as long as you go in any inertial reference frame, the force is the same. Even in non-inertial reference frames, the individual forces they do not change. Your F equals ma equations do not apply in non-inertial reference frames. Okay, there to apply F equals ma, you have to add an additional pseudo force. But one force is independent of, or any force is independent of your reference frame. However, what about displacement? Now, because position vector of any particle will depend on your reference frame. So if your reference frame is constantly moving, you realize the position vector will constantly change. Okay, even for a stationary particle. So what you realize is that the displacement of a particle depends on your reference frame. And since the particle's displacement, so one of these terms it depends on the reference frame, therefore the product also depends on the reference frame. So this quantity obviously you know is frame independent. Okay. This quantity again you will realize is frame dependent. So therefore the product becomes frame dependent. Okay. Remember that work done by a force will be defined in every reference frame, and for every reference frame it can be different. It can also be same, of course. Okay, now this work can be defined in two ways. So for a constant force, the work is defined as F dot S, and for a variable force, it is defined as the integral of F dot ds. Okay, so I'm just reminding you, I'm not going to explain why this happens. If you need any details of these, then you can watch my lectures for 2022 aspirants. Okay. Now, you will also note that work done by a variable force will usually depend on the path of the motion. Okay. So please remember that. Okay. Now, before we get started with some practice problems, as I was saying, I wanted to clarify the confusion that a lot of students have regarding what that F is, what that S is while calculating work. So let's go over that. So when you say that work is F dot S, so what is the F and what is the S that you're using? So let's go over that. So all these definitions are defined for were defined for point masses first, and then also you can find the work by any force. But the way you calculate that is, so let's take an example of a bigger body, a big body like this, okay, and it is being applied three forces. Let's say here you have a force F1 vector acting on it. Here you have another F2 vector acting on it. And here you have some F3 vector acting on it. And under the influence of these forces, let's say that the body undergoes some displacement. Okay, maybe it becomes like this. Okay, so maybe the body has moved forward and maybe it has even rotated. So maybe I can try to some more space to draw its displacement. So let's say that this is where this body landed. Okay, so somewhere here, this is what became of this body. So this point F1 where it was acting has shifted here, F1 vector. This is your F2 vector and this is your F3 vector. Now, while calculating the work, if you want to calculate the work due to force F1, then the F that you're using here is the force for which work is being calculated. A force for which work is to be calculated. Okay. So for instance, if you're talking about work done due to force F1, then you will put F as F1 vector. Okay. How about the displacement? The displacement, please note, is the displacement of point of application of that force. Okay. This is the displacement of point of application of that force for which you are trying to calculate the work. Okay, so please remember this. This is something which a lot of students either are not clear about or don't even know altogether. So, for instance, if I wanted to calculate the work done due to F1, then what you will realize is you will see the force, the displacement of the point at which F1 was acting. So this, let's call this displacement S1 vector. So work due to F1 would have been F1 vector dot S1 vector. Okay. Similarly, if you wanted to calculate the work due to F2 vector, then that would have been F2 vector times this displacement, which is S2. Let's call this S2 vector. Okay, so that is what you will realize. Now you realize if a rigid body is moving or any body is moving in a weird fashion, then different points on this can have different displacements. So let's say if pen was moving such that one force was acting here, another force was pulling it here, so it may have moved like this. So imagine if this moved like this. Okay, this moved like this, it moved forward and it rotated. Then you will realize if you want to calculate the work due to this force, then you talk about displacement of this point where this force was being applied. If you want to calculate the work done due to this force is acting on the end, then you take the displacement of that point where that force was acting. Okay, so you realize that these two displacements will be different. Okay, and for whatever force you are calculating the work, you take the displacement due to at the point of application of that force, where that force was applied. Okay, so similarly, you will realize that work done due to F2 would have been F2 vector dot S2 vector. How about the total work done? Okay, how do you find the net work done by all the forces? So net work done by all the forces. Now, a lot of students believe that this is how you can calculate summation F times displacement of Cm. This is the commonly told definition that a lot of students tell me this is wrong. That is not. So how do you find the net work? You find the work due to individual forces and then you just add them. That is the only way. Okay, so net work done by all the forces would be summation of work done by F1 plus work done by F2 and so on. Okay, so you find the work done by individual forces by this definition, and then you simply add them up. Do not use summation F times S because you realize if I'm talking about this situation, then what is the S that you will take? Every point is getting displaced by a different displacement. Okay, so you never use that. Only in two cases this tends to hold true, and that is what believes people to wrongly think that this is what you will do. See, in case of a point mass, if there was a point mass on which all these forces were acting, then yes, because the point mass will have a single displacement, or all the forces would act at the single point. Okay, so the displacement of point of application of all the forces would have been the same. In that case, you realize if you are calculating F1 dot S plus F2 dot S, then you could have taken those F's common and then you could have applied this. Okay, summation F times displacement of that point mass. Okay. In other case, if a rigid body was under pure translation, you know that every point of a rigid body undergoes the same displacement. So in these two cases, yes, this would have worked, but this is not generally true. So this would have worked if you were talking either about a point mass or for a rigid body which is translating. Then yes, because the displacement of all the particles is same, then you have one value of S. Otherwise, you realize every S can be different and you cannot in general use this equation. Okay. So I just wanted to clarify that. Let's go over a quick problem. So you've been told here a small object of mass small m can freely move over a vertical quarter circle. Now object moves from A to B under the influence of a constant force F as shown in the figure and the force of gravity. Now if there is no friction anywhere, you have to find out the total work done by force F and the gravity when it comes from A to B. Okay, so tell me quickly what the answer would be. Okay, so hurry up. Let's talk about this quickly. What do you think is going to be the answer? Okay, I would like you guys to give it a try quickly. Okay, so anybody, let me know. Okay, so AP is trying. What do you think will be the answer for this problem? Okay, great. So try and quickly answer this. Let me wait for you guys for 1 minute. Okay, D. So yes, that is correct. Very well done. A lot of students will feel that maybe it is A, maybe it is C also. But the correct answer is D. Very well calculated. So I told you that work done, the net work done, W net is nothing but work done due to F plus work done due to gravity. Now, if you talk about work done due to F, so you realize what is the displacement of this point? This point comes from here to here. So you realize this is the displacement vector. And how can I write displacement vector? So let's write that quickly. Let's write those here. So what is F vector? F vector is minus F I cap. Great. What is force of gravity vector? So that is minus mg j cap. And what is your displacement vector? Displacement vector is, you will realize it came d downwards and d towards the left. Okay, so displacement vector is minus di cap minus dj cap. So you realize work done by force F would have been F vector dot S vector. So that you will realize would be F times D. Okay. Similarly, force done work done by gravitational force, that would have been again F times D. Okay. So that is how you will realize that. So that is why we will realize that the net work done, W net, that would have been F plus mg times D. Let me just correct that. Okay. I hope everybody followed this. Okay, very, very simple. See, that is option number D. All right, moving ahead. Here is another question which should remind you that since work done by a variable force was integral F dot ds. So you realize what is this? This is area under Fs graph. This is just to remind you of that. So let's quickly try and solve this one now. So you have been told that Fx graph of for a given displacement of the particle looks like the following. So you have 1D force and a 1D displacement. So F versus X graph looks as follows. You have to find out the work done by the force to move an object from x equals 2 to x equals 6. Okay, let's try this very quick. All right. So come on, keep on trying and keep on practicing. So this is meant for quick revision of concepts and for quick practice. So after these sessions, as I told you in the last time also, what you can do is you should be uh, having a question bank with yourself, which you should be practicing to increase your speed and accuracy. Okay, so revise the key concepts quickly over here. Okay, so AP says B. Okay, so that is fast. Very nice. So that is the kind of speed that you want to aim for, and that is the correct option. So very well done, AP. So you realize at x equals 2 here, this would be 30. Okay, because this is, if you look at the graph, so from x equals 0 to 4, it reaches to 60. So at 2, it will reach 30. Then if you notice in 8 units, it reaches from 60 to 0. So in 2 units, the change would be 1/5. I hope 1/4. I hope you realize that. So in a distance of 8, the graph drops down from by 60 points, okay, by 60 newtons. So in two points, the graph would have gone down by 15, one-fifth of 6, one-fourth of 60, 15. So what will this point be? This point would have been 45. Okay, so now this is a parallelogram. Okay, or sorry, trapezium. This is another trapezium. You can find the areas of both these trapeziums. The area of trapezium is half sum of parallel sides into distance between them, and that is how you will get your answer. Okay, so the area A1, if I call this area A1 and this area A2, then you will realize that A1 is half sum of parallel sides, which is 30 plus 60 into distance between them, that is 2, so this is 90. And A2 area is half sum of parallel sides, 45 plus 60 into the distance between them, so that is 105. So the total area is 195. That is going to be your answer. This is the work done, 195 joules. Okay, so very well done. All right, great. Great to see you going very nicely, AP. All right. Next, I also wanted to quickly talk about a lot of misconceptions that students have. So again, so first is that people think that normal reaction never does any work. This is a common misconception that I've seen in a lot of students. In my live classes, at least I had seen this misconception, so that is not true. So normal reactions can do work. Okay, so as I told you, your normal reaction one is a frame dependent quantity. So even if imagine the case of a lift and you have a block kept here and the lift was going up. Okay, so you realize what is helping this block gain potential energy? It is the work done by normal. Okay, so normal can do work. In other instances, you will also realize that consider the situation where one block is kept in contact with another block like this, and if you are forcing these two to move with the help of an external force, so what is helping this guy gain the kinetic energy? The green block, it is the normal reaction. So normal reactions can do work. Okay, first of all. Next, static friction can never do any work. That is wrong. Static friction turns out can do positive, negative, as well as zero work. I have shown you examples of this. So let me quickly show you an example of that again. So if you realize if this phone is kept here, there is no slipping between my hand and the phone. So you realize the force of friction acting is static friction. So if I apply a force with which this doesn't slip, then you realize this static friction is doing zero work. Now imagine if I suddenly move my hand. If I suddenly move my hand like this. So what is causing this phone to move? It is the force of friction, right? I am not applying any other force. It's the force of friction that is causing this phone to move. And you realize that since there is no slipping between my hand and the phone, the force of friction is static in nature. So this static friction is definitely doing some work. That is why this guy is gaining speed. So it is doing positive work. Similarly, if I slow down my moving hand, so when I slow down my moving hand, then this guy loses speed. Which is the force that causes to lose speed? It is the static friction again. So static friction can do positive, negative, and zero, all kinds of works. However, this is a very important point. This will help you in your problem solving. The total work done by static friction on a system is always zero in all reference frames. So what do I mean? The system of two bodies which are applying this static friction on each other. So in this particular case, I will have to take my system as this phone plus my hand, because these are the two bodies exchanging the force of friction, right? My hand is applying friction on the phone is applying friction on the hand. So for the system of these two bodies, the net work done by the static friction will always be zero. You realize the direction of friction would be opposite on both. So if my hand is moving like this, so this block moved like this. So on this block, the friction would act in this direction. On my hand, it would have acted in the opposite direction. These two frictions are action reaction pairs. So these will have equal magnitudes, opposite directions. Now the displacement of point where this friction is being applied is same for both, right? So one will do some positive work, the other will do exactly equal amount of negative work. And that is why for a system of two bodies which are exchanging the force of friction between each other, the net work done by static friction is always zero in all reference frames. Okay. Similarly, a lot of people misbelieve that kinetic friction always does negative work. That is again not true. So again, by the same example I could have shown you, if I move my hand fast enough, then also you realize this phone would have slipped on my hand. Okay, so if I don't know if I can do that without breaking my phone, but let's try. So if I move it fast enough, so it is right now hanging ahead of my hand. Okay, and if I moved it very fast, so you realize now the phone is behind my fingers. It was initially ahead of my fingers. This got displaced. The phone got displaced, and since they were slipping between the hand and the phone, the force acting on the phone was kinetic friction. So this kinetic friction was the one that helped gain uh, velocity to the phone. So yes, kinetic friction can help you gain speed. So that means it can do positive work. However, just like static friction's net work is zero on the system, the total work done by kinetic friction on a system is always negative and same in all reference frames. In fact, here I would like to bring to your attention a fact that work done by internal forces of a system is net work done by all internal forces of a system is always independent of your reference frame. It is same in all reference frames. Okay. Next, if work done on an object is zero, then you cannot quickly conclude that the force or the displacement have to be zero. The angle between the force and displacement could also have been 90. So, in avoid making such wrong conclusions. Okay. With that, let's move forward and talk about the concept of energy. So energy is, we realize, is a mathematical quantity. It's a quantity that is associated with bodies. And what this does is, the best way to define energy is that it gives any object the ability to do work. Okay. The entire approach of work and energy rests on relations between work and energy. If you can find work, if you can find energy, the relation between them is what is helping you to solve all your problems. Okay, so let's talk a bit about energy then. Okay, so Ram Pravesh says, but there was a displacement in the opposite direction of kinetic friction. No, there you are wrong, Ram. You are wrong there. See, what was the direction? What was the direction of kinetic friction? What was the direction of kinetic friction? It was forward, right? That is why this moved forward. The phone starts from here. Let's see where the phone lands. Okay, where did the phone land? The phone landed here. With respect to my hand, it lands backward. But with respect to ground, the phone lands forward. Can you see that? It went backward with respect to my hand, but with respect to ground, it actually moved from here to here. So since with respect to my hand, it is going backward, the kinetic friction is forward. And with respect to ground, it is moving forward also. The displacement is also forward. That is why the work is positive. Okay. So I'm glad you asked that question. And I hope it's clear now. Okay. So it's good to keep asking questions. It's good to think about your concepts. That is what brings you more clarity. Okay, I hope that doubt is clear now. All right, great. So next, talking about energy. Energy, of course, is a scalar quantity and has the same SI units as that of work, that is joules. Because I said that energy is the ability to do work. So how do you measure the ability to do work? It is the amount of work that you can do. So it will have the same units as work, which is joules. Okay. Now, in work energy power approaches, you see that forces are means of transfer of energy through work. Okay. So Newton's approach of analysis of motion, we realize that forces, what they do when two bodies apply forces on each other, the forces exchange help the bodies exchange momentum, right? So that is the difference between the approach of work power and energy and Newton's analysis. So Newton told us that when you apply a force, so this guy will feel a minus F. Okay. So what happens is that one body is transferring momentum to another, some dp. You realize if the momentum of one object will decrease by dp, then the momentum of another object would increase by dp. The net change in momentum would be zero. So this is what Newton says, that when two bodies interact through forces, they exchange momentums. Now, work per energy approach in fact tells us that when they do work or when they interact through forces, they can transfer energy from one another. So the effect of a force is to transfer energy from one body to another. Okay, or any force helps you transfer energy from one place to another. Okay, so this is going to be our approach for work energy. Now, in mechanics, we mostly deal with mechanical energy. So normally, energy has many forms: light, heat, sound. But in mechanics, we only deal with mechanical energy, and mechanical energy has two components: kinetic energy and your potential energy. So we will quickly talk about these two components. Let's talk about kinetic energy first. What is kinetic energy? Kinetic energy, you must have read this definition. It is the energy possessed by a body by the virtue of its motion. Okay. So what do I mean by that? What is the energy possessed by a body by the virtue of its motion? You all know this formula, half mv square, right? Kinetic energy is half mv square. Why is it half mv square? Why is it half mv square? So what you can see also is that for any object moving with velocity v, it can also be defined as the amount of work required to accelerate the body from rest to the velocity v. Okay. So why are you getting this expression, and why are you calling this energy is associated by the virtue of its motion? Hi Deepak, how are you? So let's quickly tell you about that. And I will prove that kinetic energy or the energy associated with the motion would be half mv square. Quickly prove that. So see, I will tell you an example. First of all, imagine again, I will use my phone a lot for these. So imagine if this phone is kept here and this pen is kept here. So can this, okay, I don't know if you can see the pen because pen is also white. Okay, so maybe I can use a black pen. All right, so let's talk about these two. So here is a phone and here is a black pen. They are in contact with each other, but the phone is not moving. So can the phone do any work on the pen right now? No, it cannot apply a force. It cannot displace the pen. It cannot do any work. Okay, how about this? How about I change the situation slightly? So imagine if I gave the phone some motion. Okay, so if I forced this to move, so if I moved it like this, now you will realize when it was moving, a moving phone could apply a force and could displace the pen and hence do work. So when stationary bodies are there, you realize by default stationary bodies usually cannot do any work on objects. However, moving bodies can hit bodies and push them and hence do work. Now, how much work can a moving body do? So there are two ways of thinking about it. So either you say that okay, let's see if there was a block which was moving and if it had to do work on something, so it can do work until the time it's moving. Okay, but where is that ability of doing work coming from? So another way of thinking of this is that imagine if the block was initially at rest. So initially it had no motion. Okay, and finally it starts to move with some velocity v. Okay, so let's assume that. Now you realize somebody must have done some work on it in order to cause this motion. Okay, it gained speed. So if it gained speed, then work must have been done on it. How much work must have been done? We can think about that. So we realize that work would be F dot ds integral. Okay. Now F would be ma dot ds integral. Okay. Now you will also realize that m and a can be written as dv over dt dot s. Okay, now this can also be written as m times integral of v vector dot dv vector. Okay. Now you will know that dot product of v dv is in fact vd. That is what you will realize, where v is the magnitude of velocity vector and dv is the magnitude of a change in small change in magnitude of velocity. Now, if you integrate this from 0 to v, you will realize that work done is half mv square. And that is why you say that the kinetic energy, the energy associated with motion is half mv square. Because this was the amount of work that you would have done in order to move the object of mass m from rest and take it to a speed v. So you realize if this body now has to transfer this energy, has to do amount some work, this is the amount of work that it can do. This is the amount of energy it gains from work. So whenever positive work is done, a body gains energy. Whenever negative work is done, a body loses energy. So if this is the energy that the body gained by this work, then this is the amount of energy that it can give to any other body. And that is why we say that the ability to do work is this. Okay. And that is why you have the expression half mv square. Okay, I hope that is clear. So this is what I wanted to show you, that why you use kinetic energy as half mv square only. Why not half mv? Why not half mv cube? It is just logical. This is the amount of work that you would have done in taking a body from rest and giving it a motion of velocity v. So while giving a body motion, you have to do work. When this motion is there, then this body can also do this amount of work on any object before the motion ceases completely. That is why you say that because of motion, a body has kinetic energy, and kinetic energy is equal to half mv square. Okay, so yes, I think I've shown it here also. Okay, so let's move forward. Let's talk a little bit more about kinetic energy. So kinetic energy, of course, is a scalar quantity again, because work is also scalar. Kinetic energy is also scalar. In fact, you can also write kinetic energy as half mv dot v. So it is also defined as the dot product of v and v vectors. So obviously it's a scalar quantity. Now this can only be positive. Okay. So I hope you realize v dot v is mod of v square. Mod of v square can only be positive. Kinetic energy can never be negative in any reference frame. Okay. So scalar, only positive. Depends on reference frame. Of course, it will depend on reference frame. Why? Your velocities depend on reference frame. So if you change your reference frame from ground frame to a moving frame, you will realize that the object's body's velocity would appear different, and hence its kinetic energy would also appear different. Now, this is usually an instantaneous quantity only. We do not mostly talk about an average kinetic energy. We always define kinetic energy instantaneously. Now, the expression half mv square is only defined for a single point mass. Please note that. For a big object, you cannot use this. For a big object, you find the kinetic energy as sum of all the point masses. So of a body, turns out, is summation of k's of all its constituent masses. So if it contains a lot of masses, then it would be summation of the kinetic energy of all the point masses. So how do you use the term half mv square for a big block? For a big block, if a big block is translating with a velocity v, then we say that the kinetic energy is half mv square. Why do we say that? Because in most of the cases that you're talking about, the body is translating. Okay, if the body was not translating, if it was also rotating, then I hope you remember that the kinetic energy is not half mv square. It is half m vcm square plus half I omega square. Okay, so yes, that is the case. Remember that. So why are you using half mv square? Because as long as a body is translating, you will realize that at any instant, for a rigid body which is translating, the velocity of all its point masses, so any point mass on the body will be moving with the same velocity v only. Okay, so that is why you are able to use that definition for big bodies also. So here all the point masses are moving the same velocity v. So the kinetic energy of this system, you will realize the Ke would have been half mi v square summation, and since v is constant, so it would be nothing but half summation mi v square. And summation mi is nothing but the total mass of the object. And that is why for bigger objects also, you do use half mv square, but please note that half mv square is defined only for point masses. Okay. For big bodies, it may be equal to half mv square if the big body is a rigid body that is translating with a velocity v. But if it is a non-rigid body where different masses may be moving with different speeds, so for instance, you may have had a collection of two masses which are connected with a spring. You can have these, right? You could have had two masses connected with a spring. Now you realize at any instant this guy can move with v1 and this guy can move with v2. Okay, so now how do you write the kinetic energy? You write it as half m1 v1 square plus half m2 v2 square, right? You do not say half m1 plus m2 some v square. Okay, so that is the definition again. So please remember that. That's an important point. All right, so why don't we practice some problems? So let's get started with an easy one. You've been told a block of mass 5 kg is moving with a speed of 4 meter per second. Find the kinetic energy of the block in a reference frame of an observer moving with a speed of 2 meter per second in the direction opposite to that of the block. So you have a block of 5 kg, you have a block of 5 kg which is moving with a speed of 4 meter per second in the ground frame. You have to calculate the kinetic energy of this in the reference frame of an observer which is moving in the opposite direction with 2 meter per second. Okay. So in the reference frame of this observer, what will be the kinetic energy? So let's quickly have this. This is a very, very simple problem. Okay. Okay. So what is the answer going to be? Hurry up. Try this and try and give me a quick answer. Okay. Try and quickly answer. Come on, guys. Okay. So yeah, do it fast. I mean, this is a very, very basic problem. Very simple. See, no, you need to pay attention to the question. So you have been asked to find the kinetic energy of the block in the reference frame of this observer. So that is not C. The answer would be A. Okay. So you realize that what you calculated was half mv square, right? That is the kinetic energy in the ground reference frame. Okay, that is 40 joules. That is the ground reference frame kinetic energy. Here I have asked you the kinetic energy in the reference frame of an observer moving with speed 2 meter per second in the opposite direction. So in the reference frame of this observer, you will realize in our reference frame, what is the velocity? In the given reference frame, the velocity of the object, in the given reference frame, you will realize v is 6 meter per second. So therefore, the kinetic energy in this reference frame would have been half into 5 into 36. So that would have been 10 into 9. Okay, yes. 90 joules. Yes, right. Yes. Always read your question carefully, AP. That is not something where you want to go wrong. Okay, very easy question to go wrong because they make these small little mistakes. Okay, so I always tell my students that don't ever hurry up in reading a question. Always take your time in reading a question. Trust me, that time is well spent. So I know kids always want to, quickly give an answer. They don't want to pay enough attention also to the question, and that is where they end up making a lot of mistakes. Okay, so avoid that. Okay. All right. So moving forward, let's also quickly talk about the work energy theorem. What the work energy theorem is. So if you realize that if you wanted to calculate the net work done on acting on a body by all the forces, then you will quickly realize that net work done by all the forces acting on a body is equal to the change in its kinetic energy. Okay, so that the net work done by all the forces acting on a body is equal to the total change in the kinetic energy of the object. This is what you call work energy theorem. Okay, please remember that work energy theorem states that net work done by all the forces acting on a body is always equal to the change in its kinetic energy. Now, please remember that this theorem can be applied in any reference frame, whether it is inertial or non-inertial. But if you're applying it in non-inertial reference frame, then do remember to add the work done by pseudo forces. Okay. Otherwise, in whatever reference frame you are applying this, in that reference frame, the change in kinetic energy would be equal to the net work done by all the forces in that reference frame. Okay. So, two important quick points can be applied in any reference frame. This is something which people don't pay much attention to. So this can be applied in any reference frame. So this is not ऐसा नहीं है कि ये सिर्फ ground frame में लगेगा, okay? Because we generally use it in ground reference frame, so people are so used to applying this in ground reference frame. उन्हें लगता है और reference frames में ख्याल ही नहीं आता कि ये भी लगा सकते हैं. But you can apply this in any reference frame. And second thing, to apply this, to apply this theorem in a non-inertial reference frame, in a non-inertial reference frame, you need to consider the work done by pseudo forces also. We need to include the work done by pseudo forces also. So please remember that. Okay. Now let's move on to a question where we will see the application of this. So this is a great example where you will see the application of this theorem. So what is the use of this theorem? This theorem can help you easily calculate the works of forces that you know nothing about. Okay, for instance, drag force. You don't know how the drag forces act. So nobody tells you how drag forces act. Their equations can be really complicated. Okay, so however, using this theorem, you can easily calculate the work due to drag force. So here is an example. An object of 5 kg mass falls from rest to a vertical distance of 20 meters and hits the ground with a velocity of 16 meters per second. This is what you observe. You have to find out the work done by drag forces on the object. So I'm talking about air drag or air resistance. Okay, that is what you have to find. If with this information, find the work done by the air resistance force or the air drag forces acting on the body. Okay, so try this quickly. And let's see if you can solve this. Okay, AP. So I think everybody watching the lecture should try these problems along with the lecture only. It'll help you not only understand the theory better, but get a quick practice, so that you know where you may go wrong in solving questions answers. So very well done, AP again. So AP says it's B, and if I remember it correctly, I think it was B only. Let's see. Okay, so what have you been told? You've been told that a block. Let's imagine the situation. A block starts from west, falls vertically to a distance of 20 meters, and is hitting the ground with a velocity of 16 meter per second. Okay, so that is the situation that has been told to us. Right. Okay. Let's see. This height is 20 meter. So do you realize when it is moving during its motion, what are the forces acting on it? So you will see two kinds of forces will act on it during its motion. So imagine if it was somewhere in the middle. One, you will have a force of gravity acting on it downwards, G, and then you would have had drag forces, air drag forces acting on it in the upward direction, which would oppose the motion. I hope you realize that drag forces or air resistance forces always oppose the motion. Okay, so that is what you will see, that these are the two forces that are acting on it. Now, since you do not know how the drag force varies, so you can't calculate the work of drag force directly. However, you could have used your work energy theorem, because you can calculate the work done by the force of gravity. So you can say work done by gravity would have been, so the displacement is downward 20 and the force of gravity is also acting in the downward direction. So that would have been 20 into mg. Okay, so that is 1000 joules. 1000 joules of work is done by gravity. So what is the work done by drag force? This I don't know. I have to calculate this. What was the initial kinetic energy? Initial kinetic energy was 0. Let's talk about the final kinetic energy. Final kinetic energy is half into 5 into 16 into 16. So that would be 640 joules, right? So 640 joules. Now, using the work energy theorem, we can say, using work energy theorem, what I can say is that work done by gravity plus the work done by drag force should be equal to K final minus K initial. So that would have told me that work done by drag forces is in fact 640 minus 1000, so negative 360 joules. Okay, so that is the work done by drag forces. So here only the magnitudes were mentioned, that is why 360 is correct. But technically it should have had a negative sign also with it. Okay. So I'm assuming that they only asked about the magnitude, that is why we marked 360. Okay, otherwise it should have been technically given with a negative sign. So let's just add negative signs here for all our options. Okay. So very well done, AP. That is how you would have done it. Correct answer. Next, we will talk about conservative forces and non-conservative forces. So earlier we have seen two kinds of ways of dividing class or classifying forces. So one was fundamental forces and non-fundamental forces. Another was contact forces and non-contact forces. Now we are coming up with another way of classifying forces, which is conservative forces and non-conservative forces. So let's see what that is. So careful observations will show you that based on their behavior, as far as work is concerned. So this definition is connected to how these forces do work. Okay, so all forces can be divided into two categories of conservative or non-conservative. So when a conservative force does a negative work, so I told you, whenever something, you will realize this from your work energy theorem also. Positive work done by a force increases kinetic energy, or when you're doing positive work, you are supplying a body kinetic energy. When you're doing negative work, you are taking away kinetic energy. Okay, so that is another thing that you should have noticed here. And let's write that somewhere. Hmm, maybe here. Let's try and fit that somewhere here. Positive work means giving a body energy in kinetic, giving a body kinetic energy and negative work means taking it away. Okay, taking away kinetic energy. So in one form, you give a body energy, and the other, you take away the energy. Okay. So now you will notice that whenever some forces do negative work, whenever some forces do negative work, so they are taking away energy. Now the difference in the behavior happens of what they do with that energy. So negative work means taking away energy, and it's right. Negative work means taking away energy. Now you can do two things with this energy that you've taken away. Okay, you can either store it or dissipate it or spend it all away. Okay, so that is the difference between these two. Or dissipate. So what is dissipation? Dissipation means spending it, spreading it out. Okay, so you took some energy, then you threw it out. Okay, you dissipated it into the environment. Okay, so if you store energy that you take away, then you are a conservative force. If you dissipate the energy that you take, then you are a. So that is the way of classifying forces into these two categories of conservative or non-conservative. So whenever they take away energy from any system, then either they can store it or they can dissipate it. Okay, so this is the example that I give. So imagine two kinds of kids. Parents give their kids money. Some people like to save that money. Some people like to go out and spend it. So if you are the saving kinds, then you are a conservative kid. If you are the spending kinds, then you are a non-conservative kid. Okay. Now, what are the characteristics of conservative forces? Let's quickly talk about that also. So work done by conservative forces does not depend on the path followed by the object, okay, but only on the final and the initial positions of the object. Now, work done by these forces along a closed path is always zero, so remember this. Now, a mathematical function of position can be defined for finding work of each conservative force and is associated with something called a potential energy function. Now, as I said, that when conservative forces do work, their work depends only on initial and the final positions. So where they are initially, so initial position vector and final position vector. So you realize if you are calculating the work is defined as integral of f dot ds. So obviously integral from initial position to final position. How is integration done? It gives you some function g of f minus g of I. So you realize if it is independent of the path, if this integration is independent of the path, what does that mean? That means whether you take the this route or you take this route or you take this route, you should always get the same mathematical function. Okay, I hope you follow this. This is the mathematical thing to realize that if you are doing this integration and every time you are getting a result which depends on only the initial and the final positions, so there has to be a function which depends on the final and the initial positions, and this function has to be constant irrespective of what path you took. Every time on integration, you should get the same function of positions. This is what you will call potential energy function in fact. And that is why you realize you study that potential energy is a energy associated with position because mathematically this is a function of position. Okay? And your work done by conservative forces depends on initial and final positions only. So these forces are also called non-dissipative forces. Why? Because they do not spend the energy that they take away, they store it. Now the examples include gravitational force, electrostatic force, and spring forces, etc. These are all examples of conservative forces that exist in nature. Now, all constant and central forces are always conservative, so you need to remember this. So, constant force, which does not change in magnitude or direction, that is always conservative. How about a central force? What is a central force? Central force is a force which always points in a fixed direction, towards or away. okay, which always points towards or away from a fixed point. So such forces are always conservative. Okay, so forces that point towards or away from a fixed point. Okay, so that is what you call a central force. So it has a center of sorts. So it is always either directed to some central point, or away from some central point. That is what the central force is. Okay, now let's talk quickly about non-conservative forces. The work done by such forces depends not only on the initial and the final positions, but it also depends on the path followed by the object. Okay, so here the path matters, and if you take different paths, you will get different amounts of works. Now, work done by these forces along close paths are always non-zero. This is the differentiating factor between these two forces. Okay, if you go along a close path, the work done by non-conservative force is always zero. Now, you cannot define a potential energy function for these. Okay, potential energy is only defined for conservative forces. As I said, what is potential energy? See, I told you earlier, whenever conservative forces are taking away energy, they store it. Now, the form in which they store this energy, that is what we call potential energy. Okay, potential energy is the energy that gets stored when that conservative force is storing whenever it is doing negative work. So it is storing in some form. That form is called potential energy. So since these forces do not store energy, so they do not have any potential energy associated with them. Okay. All right. Next, these forces are also called dissipative forces. Non-conservative forces are also called dissipative forces because they dissipate all the energy that they take or acquire from anywhere. Examples include friction force, viscous force, air drag, etc. All these forces are non-conservative or dissipative. Okay, now let's see through two examples that work done by the force of gravity, which is conservative force, is independent of the path taken. Okay, so in one case, you are taking a body from here to here directly along this, and in another case, you are taking the same body from here to here but along this path. Okay, and you will realize that the work done by gravity would be exactly the same in both of them, and it would be minus mgh here. It would be, in fact, minus mgh here also. The path would not have mattered. You could have calculated that, and you can see this. This is very easy to see. Okay, so if this is h1 and this is h2 and this is h3, you will realize from A to here, the work done by gravity would have been minus mg h1. Okay, from here to here, it would have been minus mg h1. From here to here, it would have been zero. Why? The force of gravity would have been perpendicular to the displacement, so it would have been zero. From here to here, it would have been minus mgh2. From here to here, again zero. Here to here, minus mgh3. So when you add all the works, what you're getting is minus mgh1 plus h2 plus h3. h1 plus h2 plus h3 is nothing but h. So you realize that the work done by the force of gravity is independent of the path, and hence it is a conservative force. On the other hand, we will see another example where we will try to find the work done due to the force of friction. So let's try this example. So an object of mass m is moving in a circular path of radius r in a horizontal plane. Now, if the friction coefficient between the object and the plane is mu, you have to find out the work done by the friction force during one complete cycle. So imagine that you have a horizontal table, and on a horizontal table, this block who is moving in a circle, maybe tied to a string, or somehow it is moving in a circle. Okay, so let's imagine this is what is happening. It is moving in a circle of radius r. This is it. The block has some mass m. Okay, so when it completes one full circle, what is the work done by friction? Try this. Imagine it starts from here, goes here, comes back. So in a closed path, you want to see whether the work done is zero or not. So let's see. Try and quickly answer me. What is the work done by friction here? Okay. You will realize it will be non-zero. Okay, so try this and give me your answers. Let's see who can give me the answer quickly. Okay, anyone? Somebody should solve this quickly and give me an answer so that we can move forward. This is super easy, okay? Okay, AP says survey. So I like how active AP is. So guys, I would appreciate if everybody is that active. Trust me, that'll help you learn better and learn faster. So AP says minus 2 pi mu mgr. Yes, that is in fact correct. So you will realize during the entire displacement, the force is like this, and displacement vector ds vector is in the forward direction. Okay, so ds vector would be in the forward direction. You go anywhere, that will be the case. Okay. So anywhere you will realize in this entire circular motion, the ds vector and f vector would be acting in the opposite direction. Why? Because this is kinetic friction. Kinetic friction is always opposite to the direction of motion. Okay, so that is why you will see that this angle will exist between f and ds at all points. Okay, so you realize that work done would be minus integral of f dot ds. Now f is constant. It has a constant magnitude, which is mu mg, sorry, into ds with a minus sign. Okay, so from initial position to final position. So if you take out minus mu mg out of the equation, you have integral of ds. Now integral of ds is nothing but the distance traveled from between its initial and the final position. So between the initial and the final position, it has completed one full circle. The distance traveled would be 2 pi r. So the answer is minus 2 pi r times mu m. Okay. So I think that was the answer that AP had given. Yes. Yes. Minus 2 mu mgr. Absolutely. Okay. Very well done. So you realize in a closed path, the work done by friction is non-zero, proving that it is a non-conservative force. Okay. Next, we will talk about potential energy. And as I said, potential energy is defined as the energy possessed by a body by the virtue of its position. So this is the definition that you study, but this definition in itself is slightly incomplete, and that is why people have a tough time understanding potential energy. So simpler way of understanding this is that whenever conservative forces do negative work, then they store that energy, and the form in which they store that energy is called potential energy. Now, since the work done by conservative forces depends on the positions, only on the initial and the final positions, so that is why this energy also depends on position. Okay, at every position there will be some energy stored. If you change the position, there will be a certain amount of work that the conservative force would have done. So there would be a certain amount of change in its potential energy. Okay, that is why you're saying it is the energy associated with position. But not only position, it is actually the energy associated with a conservative force. Okay. If there was no conservative force, then you keep an object at any position, it won't matter. There won't be any potential energy. Okay. So there the definition is slightly incomplete. Okay. It's not only the position that matters, but position with respect because of a conservative force, it matters. Okay. If there is a conservative force present, then the position matters. So every potential energy comes from a conservative force. You need to remember this. Hence, it can only be defined. So defined, let's not defined, it would be defined for conservative forces. So whenever you define potential energies, you always do that for a particular conservative force. If you have three conservative forces acting on a system, then you will define three kinds of potential energies. Okay, one for every conservative force. Now, as work done by conservative forces depends only on the initial and final positions, so the potential energy also depends on the positions of the object. This is what I was trying to say. Next, let's talk a bit more about potential energy. So, change in potential energy is to move any object from position R1 to position R2 is given by delta U equals minus times work done by a conservative force. Okay. This I had already told you. Whenever a conservative force does negative work, then it stores that in form of potential energy. So if at position 1 you say the energy was U1, and at position 2 the potential energy was U2, then if in going from 1 to 2, going from 1 to 2, the work done by a conservative force, work done by a conservative force was W, or let's say minus W. Minus W, or I'm saying it did a negative work. Then you realize that this is the negative work is the energy that it stored. So I can say that the stored energy increases by this amount. Okay. So that is what I'm trying to say. How do you find the potential energies? You can say that U2 minus U1, the increase in potential energy would be the work done by, would have been WC if this was negative. In general, or let's just write as minus W. Minus W, then you would have had this. So in general, you can say that delta U is minus times work done by a conservative force. So whatever negative work a conservative force does, that is the change in potential energy that you see. If you would have gone from here to here, if you would have gone the other way, you realize then the conservative force would have done plus W, then you would have seen the potential energy decrease. Okay. So when conservative forces do positive work, the potential energy decreases. When they do negative work, the potential energy increases. The amount by which the change happens is equal to the amount of work done by conservative force, and that is why you have this definition. So where F is the conservative force responsible for the potential energy. The potential energy is a property of an entire system responsible for the conservative force. So I told you, whenever a force arises, the force arises from interaction of two bodies, right? There have to be at least two bodies which undergo some kind of interaction. It may be gravitational interaction, it may be electromagnetic interaction, or nuclear interactions. So whenever a conservative force is arising, it has to arise from interaction of at least two bodies. So whenever you're talking about the potential energy, so it is not a property of a single body, but a property of the system of the entire system of the bodies which give rise to this force. So it will be a property of both these masses if they are producing a conservative force. For instance, when we say, we loosely use this, okay, about gravitational potential energy. So if you are on the ground and if you are at a height m, then you say that your potential energy of the block we say is mgh, right? Now that is technically slightly wrong, because that mgh potential energy is not the energy of the block, it is the energy of the earth and the block system. So remember that. Technically, if somebody asks you what is the energy, energy is defined for the system of the block and earth. So though this usually does not happen, but you realize what would have happened was that if m was very massive, if m was very massive, theoretically let's assume something, and if m is a very massive thing, and its weight is, let's say, its mass is comparable to the mass of Earth, and then if this was at a height h, distance h, then if you realize both Earth and this mass would have moved. We generally ignore the movement of Earth because Earth's mass is so huge that this force, this potential energy, can provide kinetic energy to only the block, roughly. Practically, any kinetic energy that this potential energy provides will be provided only to the block. That is why we usually say it is the potential energy of the block, but that is not entirely true. Technically, the potential energy is a property of the block and the Earth system. If the block was massive enough, then it could have moved the Earth. Okay. Again, let's talk a bit more about potential energy. To define the absolute potential energy, you need a reference point where you assign a zero value. So please remember this. The previous definition only talks to you about the change in potential energy. So change in potential energy you can easily see. But what happens if you have to define absolute value? So what is the value of U1? What is the value of U2? For that, we choose a reference point. We will say, okay, I will assume that there is a reference point. So it is something like saying, imagine this. Imagine if I talk to you about the distance between these 2 points. So distance between these 2 points, obviously you can measure. But if I ask you to tell me the coordinates of these 2 points, then to assign the coordinates, you need a reference point. You need an origin. Okay, where you choose your origin, that will decide what the coordinates of these 2 points are. But do you realize if I choose different origins, would that have any effect on the distance between them? If I chose this, or let's say if I chose another coordinate system here like this, so you realize by choosing different coordinate systems or different origins, the coordinates of these points do change, but the distance between them is independent, right? So similarly, when you're talking about the change in potential energy, now change in potential energy is independent of your choice of reference point. You can choose the reference point to be zero anywhere; it does not really matter. The change in potential energy is independent of that. However, if you were to talk about the absolute potential energy, then you need that reference point. Okay. So how do you choose that reference point? So you can choose any reference point as you feel like. Okay. And you can assign that a zero value, and the corresponding values will be obtained by saying that you at any point P. Okay, I hope you realize that. Imagine that you chose this as a reference point and you said here u naught, and this is point O is zero. Now you have to calculate the potential energy at point P. So what you can say is that U at P would be equal to the work done, negative times work done by the conservative force in moving the object from 0 to point. Okay, that is how you can define the absolute potential energy by this definition. Okay. Absolute potential energy of any object is defined as the negative work done by a conservative force. Okay, so this I have already explained. And now let's take a look at certain potential energy functions. So you can use this definition and you can find the equations of potential energies of different forces. So for gravitational potential energy, we usually take the ground as the zero level. Okay, you say that this is where you will call your gravitational potential energy to be zero. Then you will understand that if I take a block and I raise it to a height h, okay, starting from the ground, doesn't matter where it was on the ground, doesn't matter where it is at height h, as long as it is at height h. So what is the work done by gravitational force in moving it from here to here? So in going from here to here, work done by gravity. Okay, so let's write a WG. Work done by gravity is minus mgh. Okay, now we will go back to this definition that we use right now. And what is the potential energy at P? So we know that potential energy at P would be minus times work done by gravity between O0 point and point P. You realize it is plus mgh. That is why you say that at a height h, the gravitational potential energy of a body would be mgh. Here the reference point has been chosen as the ground. Now please note that you can choose a different reference point and define different potential energies, and your problem solving will not get affected. Why? Because in problem solving you mostly talk about the change in potential energy. And as I said, the change in potential energy is independent of your choice of a reference point or your 0 point for the potential energy. Similarly, spring, in case of spring, what we do is we choose u equals 0 at the relaxed length. If the spring is a relaxed, then you choose u as 0 if this is at its relaxed length L naught. Now, if you increase the length of the spring, let's say by applying a force, then you realize that if you apply a force here, let's say, and you stretch this by an amount of x, or even compress it by an amount of x, you will realize that at any extension or compression of y, let's say in the middle, when it is displaced by y and it has to go further by dy. At this point, the spring force would be spring force at y at F equals y. Spring force is minus ky. Okay, so dw, work done by spring force, would be minus ky dy. You integrate that from 0 to x, you will get minus half kx square. Now, even if you are compressing, the answer would be the same because the force and the displacement would be in the opposite directions. Okay. So you realize since the work done by spring in moving it from the 0 point to another point P is minus half kx square, so energy at point P. So the potential energy here at point P, how much will that be? U at point P would be plus a half kx square. So this is the expression that we commonly use, half kx square. This is when we have chosen the reference point or the zero potential energy point to be at the natural length of the spring. Okay, remember that. Now, other commonly used potential energies include elastic potential energy and electrostatic potential energy. We will talk about them in detail later. And this is where I would like to wrap up today's session. And next time, we will talk about some problems with potential energy, how to calculate potential energy, and the other topics that are left in the topic. Okay. Since there is only one question, okay, so this is your homework. Try this, and we can discuss this in the next class. Okay. So you've been told an object is under the influence of a conservative force given by ax plus a b. Okay, so this is the force, and I'm telling you that this is a conservative force where a and b are positive constants and x is in meters. So this is acting in I cap. This is a 1D force acting in I cap. Okay, and you've been told find the change in potential energy of the object when it is moved from x equals to 1 to x equals 2 to x equals 4. What is the change in potential energy of this object under the influence of this force? Okay, this is your homework problem. You can try this. We can discuss this in the next class. This is where I would like to wrap up the first class. We will continue this discussion tomorrow, and tomorrow we will wrap up this discussion so that next class we can move forward to the next topic. Tomorrow we will not only wrap up the discussion of theory, we will also take up some previous year JEE Mains problems. Make sure that you're attending this session live tomorrow as well. All right. And before I leave you, let me remind you that if you want to get yourself top ranks, if you want to give your JEE preparation a boost, then this is what you can do. You can go and get yourself the Plus subscription. How do you get that? Go to your Unacademy app, go to the Plus section, select your goal as IIT JEE, and click on that Get Subscription button. You'll be redirected to the payment page where you will have an option which will say you have a code where you can write RD Live. That is my code. If you like my lectures, if you like to enroll in my Plus courses, then you can use this course, get your subscriptions, and meet me on the Plus. And you can click on Proceed to Pay. Now, these are the 3 courses that are currently ongoing and are being taken by the JEE English team on the Plus app. And then there are 4 Plus courses which are being taken for class 12 students. So total 7 courses are currently running on Plus by the JEE English team. You can get yourselves this subscription and be a part of those courses. Again, if you like today's video, then don't forget to press the like button and share it with all your friends who are looking to revise their JEE for their JEE. Okay. So Unacademy is providing you this quality content absolutely free of cost for those of you who can't afford this subscription. Unacademy believes that it is every student's right to have access to good quality education. So they are not only bringing you those Plus subscriptions at a very reasonable price. For those of you who can't afford that, we are providing free quality content. So make sure this reaches to more and more students so that most people can benefit out of this. PDF notes of the slides used in today's lecture would be available for download very, very soon. Also, don't forget to press the bell icon to receive notifications of all the lectures and sessions happening on the JEE English channel. Okay. Don't forget to connect with us on the Telegram app using this link so that you are always aware, because a lot of times students tell me that they don't receive timely notifications from YouTube. So be a part of this group and then you will always receive notifications in time. Now, before I take your leave, let me remind you one last time, this is my code RD Live. You use this code and get yourselves a 10% off on your next Unacademy subscription. So that's it from my side. I will see you guys tomorrow where we will carry forward our discussion. By the way, one more important reminder. So today at 8:30, we will have that Olympiad session. Olympiad / Pathfinder session. So where I will discuss problems from Pathfinder physics book. Okay, so if you want to join that, if you are preparing for advanced or Olympiads, then you can join me there and we will discuss some very, very interesting and very tough problems. And today, in fact, the topic is work power energy. So come join me at 8:30 and let's have some fun discussing some really, really interesting problems. All right, so see you at 8:30 then, or in case you are coming tomorrow, then tomorrow. And till then, you guys keep